yesterday. So in particular, if you look at the schedule here, you'll find a new entry on the day one material. And this is where we'll be putting each of the materials from the day at the end of each day. So if you click onto resources, you'll be able to find the recording of the session yesterday, as well as all the code that I showed live in R. So I'll click through here. You'll find the day one workshop materials that Bahman has uploaded to YouTube. And you can also download all of the code from the previous session by clicking this link. At the end of the workshop, I will add a download button up the top here for all of the lab code as well. But currently that would be incomplete, so I don't have it here. Was there anything else you wanted to mention about the website here, Bahman?
Not really, no, just that was the only thing. Thank you.
Fantastic. So yesterday we had a look at what time series is, the meaning of forecasting, and we also looked about how we represent time series using the Sybil time series object. And we looked at the index variable, which was where we represented our time information. And we also represented our key variables to uniquely identify a time series. And the things that we were interested in predicting, or the other information that we're using to make our forecasts, were contained in the measured variables. And we gave you a few tips. Usually the index variable, the time variable, looked like time. Maybe it was a daily data set, monthly, or something else. The key variables were usually character vectors or categorical variables. And then the measured variables were usually numeric, something that changes continuously over time. We then went on to look at the different time series patterns. In particular, we focused on trend, seasonality, and cycles. And we spent quite a lot of time thinking about the difference between trends and cycles. And we looked at these very common time series patterns using a variety of plots. In particular, we looked at time plots, season plots, sub-series plots, and ACF plots. Just as a bit of a refresher, I will show you again what each of those plots looked like. Okay, it looks like it's taking a bit of time to load here. So here was an example of the time plot, which is the standard approach, the simplest approach to visualizing a time series, where we put the value that we're interested in forecasting on the y-axis and the x-axis representing time. And then we played around with this x-axis a little bit to get a better look at seasonality. So by wrapping over years, we were able to see which quarter corresponded to having the maximum amount of production for a beer. We then saw season plots for very frequent time series observed every 30 minutes, and that posed some additional difficulties, but also revealed a lot more complex patterns in the dataset. We then, instead of wrapping over years, we wrapped over quarters to give a sub-series plot. And this was especially important for seeing how the seasonal pattern might be changing over time. So the beer time series here, we could see that Q4 was decreasing, while Q1, 2, and 3 were fairly flat. We then finished by having a look at an autocorrelation function plot, an ACF plot that looked like this, and we were able to identify all of the patterns that we'd discussed, trends, seasons, cycles, and autocorrelations with this single plot. So this plot is particularly useful when it comes to identifying the patterns, the temporal patterns that exist in the data that might want to be modeled later for forecasting. And then to finish off, we looked at white noise, which is what we hope to have when we finish modeling on day 3. If we were able to remove all of the patterns from a time series and end up with errors from a model that looked like white noise, that tells us that we've captured all of the information that exists in the data, and our forecasts hopefully will be quite good. Now, there's some caveats about that, but we'll look at that in a few days' time. So today we're going to continue in the direction of visualizing our time series and better understanding the patterns that might exist within it. But we're going to need to start by learning about different transformations that we can do for our dataset. These transformations are often a necessary step before estimating any models that we can use for forecasting or decomposition. We'll look at our first model today. And then in the second session, we'll have a look at alternative ways of visualizing data when you've got many time series. Maybe you're working with 100 different time series or more, and that becomes very difficult to visualize using the techniques that we saw yesterday. If you add 100 of those time series plot lines, you'll have a very difficult time seeing any patterns. If you can see any patterns, it's probably from the larger time series, and most of the patterns will be washed out and you wouldn't be able to see them because they're all plotted on top of each other. So we'll have a look at visualizing the feature space and computing summary statistics across the time series to get a good idea of what's happening in large collections of time series. I see a few questions that have been put in the chat, so I'll spend a bit of time answering these. Once again, we've got enough time for questions, so please do ask in the chat if you have any. One question was about visualizing data on the beer time series, and you get an error most of the time. If you put that error in Slack, the error here that I see, the variable does not exist. This might be because you haven't set up your data set correctly. So let me go back to an example from the previous day. So we have Oz production, and then you piped it autoplot beer. I load FPP3. Remember the FPP3 package, sorry, let me switch to R. I'll load the FPP3 package. We had Oz production pipe into autoplot to produce a time series plot of the beer column. A common mistake, which might be where you're having this issue, is if you just type autoplot beer, it can't find the beer variable. And that's because beer is a column within the Oz production dataset. So the usual way that we produce a time series plot is to first pipe in the dataset to the plotting function. That will allow you to get access to the beer column and visualize it. If you're still having trouble with code and running into some errors, feel free to put it in the chat, but do copy your code and your error. That will really help us answer your question. And if you're still having trouble, even after the sessions, you can ask your questions on Slack. Okay, let's make a start with the day 2 material. And just like yesterday, we're going to start by loading in the FPP3 package. And this package will provide us with all of the basic packages, tools, and datasets that we need to complete today's materials. So as mentioned before, we're going to start by looking at how we transform our time series. And transformations are really useful for simplifying the patterns that exist in the data. Remember yesterday when we worked with a multiplicative or an additive time series for seasonality? The transformations here are really useful for stabilizing those changes, that variation in the seasonality. So there's a bit of math here, but I will show you the plot instead. There's various transformations that we might like to use. These are all power transformations and a log transformation here, but they have increasing strength. And we'll come back to this later when we introduce a different type of transformation, which allows you to go between them all. So a quick question. I'm not sure if we have polls set up in Zoom. We don't. Put in the chat, is this time series additive or multiplicative? That's right. It seems like everyone has the right idea for this time series. Everyone has said that it's multiplicative, and that's correct. The reason why it's multiplicative, if you may have forgot from yesterday, when the value of the series, when turnover is low, so down here, the fluctuations, the variation, that means the little changes, are small. However, when turnover gets bigger, over here, you can see the seasonality and the fluctuations are much larger. Now this means that we have a multiplicative time series, multiplicative seasonality. Now imagine if you were trying to create a model, if you're trying to describe this shape that grows, that gets bigger, it's going to make for quite a complicated model. So it would be much simpler if we could modify this data set in a way where our seasonal pattern is now additive. And that's actually easier than you might think. If instead of plotting turnover, I instead calculate the square root of turnover, you can see I make some progress. Now the smaller values down here are a little bit bigger, and the big values for turnover, the fluctuations, the variation has become smaller. So I'll go between them again. Here's my original data. You can see that the fluctuations at the start of the time series, when turnover is low, is very small. And when turnover is larger, we have very large fluctuations. But if I use a square root transformation on the data, the variation is very similar. It's still a little bit bigger at the top, but they're much more similar throughout all of the time series. What if I applied a stronger transformation? Instead of a square root, I'm now using a cubed root. You can see now it's even closer to having the same shape. It looks more like an additive time series now, doesn't it? And in fact, if I go one step further, if I use a log transformation, now all of the seasonalities look like they have the same size. And this will be much easier for us to model and forecast and further analyze our time series. So transformations can really help to simplify some complicated patterns here. And in fact, we can go even further than a log transformation. If I use an inverse transformation, you see I've got 1 divided by turnover now. I've just put a minus sign so it's going in the same direction. If I do an inverse transformation, you can see I've got the opposite problem now. When turnover, or inverse turnover, is low, I have very large seasonal fluctuations. Whereas when inverse turnover is larger, I now have really small fluctuations. So we need to find some balance here. We've got our original time series and then our transform time series, and we need to find the strength of the transformation, which makes for an additive seasonality. This will make our time series simpler to model and make our forecasts better. Now, for this sliding window, there happens to be a family of transformations called Box-Cox transformations that puts in this lambda parameter. If lambda is equal to 0, we have a log transformation. But if lambda is not equal to 0, we use this pretty complicated looking equation. But let's break it down. Let's play around with specific values of lambda and see what the Box-Cox transformation is. So let's see what happens when we set lambda equals 1. That should be pretty simple. We use the sine of yt, so if it's positive or negative, multiplied by the absolute. So this sign is just keeping it negative if it was originally negative, or making it positive if it was originally positive. We have yt to the power of 1. Remember, lambda is equal to 1. Minus 1 divided by 1. So this all collapses down to yt minus 1 when lambda is equal to 1. And yt minus 1 is pretty much doing nothing. A shift by 1 up or down in the time series is not going to make any difference to the model that you estimate. So in effect, when lambda is equal to 1, we have no transformation. We're just using the original data, roughly speaking. What if lambda is equal to a half? If lambda is equal to a half, we have yt to the power of a half minus 1 divided by 2. Now the important part here is this power term. Yt to the power of half, that's my square root. So I'm taking the square root of the data, minus 1 divided by 2. The minus 1 again does nothing, it just shifts the time series up and down, and the divided by 2 just squishes the time series. This squishing, this scalar multiplication, still does nothing to the model. So we can either stretch out or flatten our time series, or we can shift the time series up or down, and it makes no difference to the resulting model. What the important part of this equation is just this power of lambda. And that's why this is known as a power transformation. So here's a summary here. Lambda is equal to 1 will give you no transformation. Lambda is equal to a half will give you the square root. Lambda equal to 0 will give you this first case, just the log transformation. And lambda equals to negative 1 will produce yt to the power of negative 1. It'll inverse the data. You can also, you don't have to use these round numbers like 1, a half, 0, negative 1. You can use something like 0.136. It's a very flexible way of controlling how strong your transformation is. And we'll use Box-Cox transformations a lot to simplify the patterns in the data. So looking at that time series again, here we have the Box-Cox transformed data, but we start with lambda is equal to 1. And I might have to switch over here. Let me see if I can get this animation to work. No. Just bear with me while I switch this across. Okay, so if I press play here, you can see lambda is going from 1 towards 0. And as we get stronger and stronger, you see the shape of the seasonality begins to change. We start with a very multiplicative pattern, and then by producing a stronger and stronger transformation, you see the seasonality looks more similar. And let's try and press pause at the right spot, maybe here. Lambda equals 0.06, we now have our seasonality having the same size for the entire time series. So we want to find a lambda parameter that produces the simplest time series possible. And to answer a question that I've seen in the chat, why do we need this transformation? The simpler we can make our patterns, the simpler our models will be. And we really like simple models. Simple models tend to be more accurate and they're less complicated. So there's less chance for things to go wrong. When we come to decomposing our time series so we can get a better look at the trend and seasonality in the data, having a simple time series is very important. In fact, it's required for the model that we'll introduce for this. Okay, I'm going to switch back to full screen now. Give me a moment. Okay, there we go. Now, there's actually a way that we can even calculate this lambda value automatically. It's called Guerrero's method, and we'll be looking at the features function more later. But you can see the resulting optimal lambda is about 0.09. So just doing it myself with a bit of guesswork, I got very close, 0.06. The amazing thing about these transformations is that 0.06 is close enough. It's not very sensitive. You can get within 0.1 plus or minus, and you'll still have a good transformation. So while the automatic method is nice, sometimes it can give you some trouble, so you should always check the results using a plot. Often if you have very small values of lambda, like -1, or if you have very large values of lambda, like +2, you might run into some problems. But when it's around 0 or 0.5 or 1, it's a good indication that this method has chosen a good value for you. So here's what it looks like with the optimal lambda. And comparing this plot with lambda equals 0.09 to the one before, they look very, very similar. So I'd be happy with either of these. In fact, when we have a lambda value that is close to 0, we tend to prefer to just use 0. We tend to like to use simple transformations like a log transformation, because that keeps things simple and explainable. If we've got 0.09 or 0 exactly, it won't produce much difference in the resulting transformed data. So to summarize transformations, often we don't need a transformation. If your lambda parameter that you find is optimal is like 0.8, 0.9, you often don't need a transformation at all. So we prefer simplicity. If you can get away with not doing any transformation, then that's good. Or if it's close to 0, it's nice to simplify it to use a log transformation instead of a Box-Cox transformation. If you have a very strong transformation, maybe your transformation is a log transformation or -1, -0.5, that will have a large effect on your intervals when we come to forecasting. You'll end up with very large intervals. So that can be disadvantageous depending on what you're trying to do with your model. If you've got 0 or negative data, you need to have a positive value of lambda. And importantly, if you do have data with zeros in it, you might find the log1p function useful. What this will do is log plus 1 of the data. So all of your zeros, rather than doing the log of 0, which doesn't work, you'll instead have the log of 1, which works much better. Another advantage of doing these transformations is that they can force the forecast to be positive. So if you're forecasting the number of people in a country, you can't have negative people. And so using a transformation is a simple way to make sure that you don't produce negative forecasts. And lastly, these transformations need to be undone. So when we produce a forecast, we're not forecasting the log of population. The log of population isn't that useful or interesting. Instead, we're more interested in forecasting population. So we like to do transformations to simplify the data before using the model, but we want to know what the forecasts on the original scale, on the original data. So this is handled automatically by Fable, so it's not something you have to worry about much. But when you do a log transformation and produce forecasts, those forecasts will automatically be undone. The transformations will automatically be undone using the exponential function to produce forecasts with the original data scale. So all of the transformations we've seen, square root, cubed root, Box-Cox transformations, log transformations, the forecast from these will be automatically fixed up to be on the original scale. Okay, we have another question in the chat. After forecasting with transformed data, we have to apply the transformation to the forecasting values, or are they realized forecast values? I think I've just talked about that, fortunately. So the forecast that you get from Fable, which we'll see later, probably tomorrow, will be automatically back transformed. Thanks for the question. Okay, so there's not just mathematical transformations that are possible. Often we're interested in estimating statistics that we can compare across countries. So these are transforming the data to be on the same scale, even though the source of the data might be different. So very common, we might do per capita adjustments. And this is in the global economy data set. So I'll actually switch back to R and show you this live. So we saw yesterday the global economy data set, which had yearly data and 263 countries, and we focused, I think it was on GDP. But we've got, maybe it was population, but we've got other variables in this data set that we might be interested in. What about GDP per capita, which is a useful indication of the wealth of a country? So perhaps I'll filter out a specific country. For Bahman, for Bahman, I will select the UK. There we go. So I've got a single country pulled out here, and I can plot the GDP. And then I might be more interested in how the United Kingdom compares to my country, Australia, which you can see follows a similar shape. But if I plot them both at the same time, by using the in function, so if country is either the United Kingdom or Australia, I'll plot both of them now. Oops, missing an extra bracket on the end there. If you ever see the plus, let me go back and show you that actually. If you ever see the plus function or the plus operator in your console, it's waiting for more inputs. So that's a common sign that you've made a mistake, like forgetting a closing bracket. You can also see the red cross here saying that there's a missing bracket to close the open bracket. So I'll put that back in here, correct my mistake. But when I run this code again, you can see I've still stuck with this plus. I can't run this code for whatever reason, or at least it will error eventually. If you press the escape key when you're in the console, maybe I'll show you that again. If you're stuck with this plus, just click down here and press escape, and it will cancel that line of code that wasn't working correctly. Okay, plotting both United Kingdom and Australia on the same plot, you can see that the GDP of the United Kingdom is larger than Australia. But this is on different scales. We've got different populations. A larger country, of course, has a larger GDP. Maybe if I plot China and Australia, two big trading partners in the world, you can see you can barely, well, I'm blocking it, but you can barely see the data for Australia because China's GDP is so much larger. So a useful transformation to make these data sets, these countries more comparable, is to scale by population. So population happens to also be in this data set, in this column, the measured variable. And I can modify my plot to be GDP divided by population. And now these plots are more comparable, and we can see that the GDP per capita, or in other words, the GDP per person, is very similar between Australia and the United Kingdom. If I add in China here, you can see the GDP per capita of China is much lower than Australia and the United Kingdom historically, but more recently, the GDP per capita of China is increasing quickly. So this tells a much better story, a much more informative story perhaps, than just the overall GDP of a country. Both of these figures are useful to understand the influence of these countries in the world, but scaling or transforming the data by other variables like population can be useful. Another useful transformation is to adjust for inflation. So there's a lot of code here, and I'll create this for you live and perhaps make it a little bit simpler. But the idea for this is that the value of money changes over time. Often the value of money decreases over time because of inflation. So if I look at the Australian retail data set, We have the total turnover for various industries in Australia by state. And if I focus on the print media industry, I'll figure out what that is exactly. Distinct industry. Remember this trick from yesterday to see all of the options for the key variables. I want to see newspaper and book retailing. So I'll copy that and filter just that industry. So now I've only got 8 time series, 1 for each of the states in Australia. And then I'm going to summarize the total turnover across all of those states. So now I have the total turnover for newspaper and book retailing in Australia. And I'm going to call this AusPrint. We can have a quick look at AusPrint. Looking at this data set, we can tell a bit of a story. What patterns, you can put in the chat, what patterns can you see in this time series? Do we have trend? Do we have seasonality? Do we have cyclical patterns? Can you tell me a bit more about these patterns? Is it multiplicative trend? Multiplicative seasonality or additive seasonality? Is the trend global, meaning it has the same trend for the entire time series, or does it change? Have a look at this time plot and let me know what you think. Oh, the x-axis is blocked. There's not too much to see here. It's just 1990, January, 2000, January, but I suppose it will help to tell you this story. This is 2010. Okay, so you're all correct that we do have some seasonality that is multiplicative seasonality. Again, we can see multiplicative seasonality because when the turnover is low, we have small seasonality. But when turnover is much larger, we have very big seasonality. And this one's interesting because you're also correct that we have a trend component, but the trend changes. Towards the end of the time series, turnover starts decreasing, and the seasonality is also decreasing in size. So important to note from yesterday, we talked about multiplicative being a function of turnover, or the y-axis, not time. And this is especially true here. As turnover increases, we get larger seasonal shapes, and when it decreases, we get smaller shapes again. So we do have a trend. It increases up till about 2010, and then it starts to decrease. That's this point here when it changes. And we also do have some cycles. There's a little drop here, for instance, short drop here. So there's some subtle changes, some drops, meaning that we do have some cyclical behavior as well. But this is in dollar terms. If I added the label properly, I have a Y label here, which is turnover in millions of dollars, in Australian millions. So because this is in monetary value, the value of the money in 2010 is lower than the value in 1990. So how can we tell when the trend changed in real terms? For this, it's useful to do a transformation using CPI. So you can see the CPI here, we've divided by that. But this data set doesn't have CPI. Remember, our AusPrint data set just had turnover. So this is where it's useful to use multiple data sets. Here I have global economy, and if I filter out Australia, and I'll save this as Aus economy, I've now got my single country for Australia. you can see that we have the CPI information from 1960 onwards. So it'd be nice if we could join these two data sets together in order to get a nice consistent estimate for the real value of the print media industry. So now if I look at Ozprint, we'll notice that we've got a bit of a problem, or at least a challenge. Our print media dataset comes in monthly, but our CPI is available only annually. Now this isn't such a problem here. We'll just use the same CPI for the entire year of the monthly data. And to do this, we need to join the two data sets together. So with Ozprint, we will mutate the data to add a new column called year, which will be the year of my month variable. So I've taken my index column, my month, and just calculated the year that that month was in. So 1982, I have my number. And then I can use this year variable to join up the data set with my Australian economy year column. And if you're not familiar with join operations, the Learn Our materials that we introduced yesterday on the website present a really nice introduction to join operations. So if this is a bit difficult for you, you can ask your mentor or have a look at the Learn Our materials. But we're going to left join the Oz Economy dataset onto my Ozprint dataset. And we're going to join these two datasets using the year column that we created. And what we now have is our original Ozprint dataset with time and turnover, but we've now added in extra information from the economy. So we have the CPI, we have the population. It's not shown in the table output, but we have population as well. We have GDP, and this opens up a lot more possibilities for modeling turnover, forecasting turnover, and also just looking at it and making some observations. In particular here, I'm interested in plotting the turnover of the industry divided by CPI. This will adjust for inflation, so we have a consistent value of money. And this tells a completely different story. Have a look at the trend in this data set now. Is the trend ever increasing? No. In this data set, it starts in 1982, but from the start, there's been a gradual decline in the turnover of the newspaper industry until recently in 2011, when it drops much, much faster. Comparing these side by side, which has been done in the slides, a bit of extra code for that, we can see two different stories. The original data, which I'm blocking a little bit here, you see it says turnover just here. The original data looks like it was increasing. Maybe the industry was going well up until 2010. But after we adjust for inflation, you can see that the industry has always been declining in value. Any questions about transformations and inflation adjustments or per capita adjustments? Okay, if you do have any questions, feel free to use the Q&A option to add your question. An important thing to note, we talked a little bit about the box-Cox transformation and the log transformation and forecasting. The challenge with this, with using extra information for the transformation, like population or like CPI, is that when it comes to back transforming the data, say if we make a forecast, we need to know the future values for CPI and the future values for population. Otherwise, we can't undo this transformation into the future. Now, some variables are quite easy to forecast, like population, and that's not such a problem. But CPI could be more difficult to forecast than turnover. And we'll be revisiting this problem tomorrow when we estimate our first models. Okay, let's now think about a different way that we might adjust our time series. And this involves splitting up the time series into its parts. We've talked about the patterns of trend and seasonality, but we've been able to look at that. We've been able to look at that only with a single plot, with a single line. But it's actually possible to split apart the trend separately from the seasonality, which makes it much easier to look at. This process is known as time series decomposition. So the type of decomposition that we're going to talk about today is an additive decomposition. And an additive decomposition will split up your data set, which is YT, into three components: the seasonality, the trend, and whatever's left over, which we know as the remainder. Now, this additive pattern is important, and it relates to the transformations that we've talked about just before. If you've got a multiplicative seasonal pattern, that means that you've got seasonality times by trend. And so we can't use this type of decomposition to look at that data. We can't split up multiplicative seasonality. There are other methods that allow you to decompose multiplicative patterns, but they have their own problems. So we usually like to use this type of decomposition. The reason why an additive decomposition isn't such a problem if you have multiplicative data is because we've just learned how to convert multiplicative patterns into additive ones. We can use a log transformation, a Box-Cox transformation, whatever transformation is needed to transform our multiplicative seasonality into an additive pattern, which can then be decomposed using this method. And the model that we're going to use to decompose that data into the components is known as STL, Seasonal and Trend Decomposition using LOS. LOS is localized regression, and how that works we'll see shortly. It uses rolling windows across your time series in order to get local estimates of the trend and seasonality. So this allows both the trend and the seasonal component to change over time. So if we're working with that beer data set where the Q4 was decreasing while the other ones were staying the same, we can decompose that using this model, the STL decomposition model. And the amount of change that's allowed over time can be controlled by choosing the size of that window. A big window will give you a very smooth decomposition, a very constant seasonal pattern, whereas a very small window will allow the seasonality to change very quickly. Now, there's other benefits to using this method. It can work with multiple seasonal patterns, but it can't work with trading day effects or holidays, and it is only additive, but this isn't such a big problem for us. Okay, so we've seen this data set yesterday, and we'll have another look at it in R now. So let's switch back over to R and have a look at US employment. And here I'm going to focus just on retail trade. So I'm going to filter the title to be retail trade. So now I just have a single time series and quite a long history here. It starts in 1939. So if I autoplot employed, you can see I have a very long history. And just to simplify things, I'm going to focus on 1990 onwards. So month is greater than or equal to January 1990. What patterns can you see in this time series? Okay, that's right. We do have a seasonal component and it is additive. We can tell that it's additive, at least for this section of the data, because even though employed might go up and down, the size of the seasonality stays the same. If I go back and look at the entire history, you can see that it might be slightly multiplicative. You can see it's slightly smaller here than up here, but we won't need a very strong transformation to make it multiplicative. So for this section of the data, you're correct. This could be considered additive. We also have some trend. The amount of employed people in the US is generally increasing. And we do have cycles. You can see that there's a drop here after 2008. Does anyone know why we have a drop here?
Financial crisis.
That's right. We had the global financial crisis of 2008. And so we had a sharp drop in the number of employed people. And so this is a cycle because we expect that there's probably more economic problems to come. We just don't know when they will be or how bad they will be. So we expect that it to continue to increase, but there'll probably be another drop sometime in the future. So here in this time series, we have it all. We have trend, seasonality, which happens to be additive, and we have cycles. But I'm interested in seeing what this seasonality looks like. So if I tried to plot the seasonality using ggseason, we can see that the peak is at the end of the year. I'm blocking the month, but it says December here. So the peak is in December, and the minimum might be in February. Can anyone guess why the minimum might be February here? It's a pretty common problem. Another type of transformation that we might use. There's less days in February. So this might not apply to US employment. This is not saying much. But very often you'll see less values in February. If I have a look at print media again, it's a bit of a detour, but I think it's interesting. So if I plot a season plot of the print media, we can see a large increase in December, but in February, there's some drops here that are uncharacteristic. And that's because we have only 28 days. So another useful transformation is to divide by the days in month. And we'll see this in the exercises. So after dividing by the number of days, you can actually see that there's more sales in February at a daily frequency. The average turnover in February is higher than January and March. So just an interesting detour. I'm not sure it applies to this time series because this is probably the total number of employed people, which doesn't matter based on how many days there are in the month. Okay, so back to this data set, you can see the seasonal plot here. It's a bit tricky to see because it's so spread out. The reason why it's stacked on top of each other like this is because we have an increasing trend in the data set. Whereas we want to focus just on the seasonal pattern and how that might change over time. So it's really nice to be able to remove the trend and just focus on the seasonality. And to do this, we can use an SGL decomposition. Now this is the first model. We'll see a few models this week, but the first model that we see is for decomposition. And to estimate a model, we need to train the model on data using the model function, and then specify the model using the STL function for an STL decomposition. Tomorrow we'll see some other types of models that can be used. But for today, we're just going to use this approach. Model STL of the variable we want. So I'm going to save this as my decomposition model. So we have US employment, piping this into the model function. And then I'm going to estimate an STL model using the employed variable. So you can see I get a Mabel from this. A Mabel stands for a model table. It's very similar to a Tibble, but it has the same key variables that you find in a Sybil. And the column here contains an entire model that matches this time series. And what we can do with this model is extract the components using the components function. And then what we get is a table, which stands for a decomposition table. And this is very similar to a Sybil, where we have the time variable, month. We have the key variables, series ID and the model used to produce the decomposition. But we also have some extra information. We understand how the time series was split up into its parts of trend, season, and remainder. And for this decomposition, you can see, just like we saw in the slides, we have an additive decomposition. What I can do with this is use it like a normal Sybil. So I have my original employed data. So I can autoplot employed. But you'll see when I plot the data, I get a slightly different view of what's happening. Rather than just getting the original time series, which I see at the top, I get 3 additional plots for the 3 components that have been split up. So I've got employed in the first facet, trend in the next facet, seasonality in the third, and finally the remainder, whatever's left over. And you can see I've managed to separate the trend by getting a nice smooth line that's generally going up, but it also decreases. So even though this says trend, it's actually meaning the trend cycle component, both trend and the cyclical part. And we've got my seasonality showing here without any trend. And you can see that this is changing a little bit over time. The peak is getting shorter. It's decreasing a little bit. So what I can do with this decomposition is use a season plot, but instead of plotting the original data like I did before, which I can still do, instead of having the trend here, I can instead plot just the seasonal component, GG season, of the seasonality. And now I can get a much better view of what's happening in the seasonality because I don't have the trend. And what we can see is that in September here, I'm blocking it a little bit, in September, originally we had the orange color. This is the start of the data. But towards the more recent years, the values have been decreasing. We see a change in the seasonal shape. Similarly, in December, it's also been decreasing. So we get a very clear idea of when the peak and the trough are by first decomposing the data and then looking at season plots. Now, since I was talking about changes in seasonality, it's also nice to look at a subseries plot. So I'm going to use GG subseries, but instead of looking at the original data, I'm only going to look at my seasonality component. And there you can see September, in the September facet, has been decreasing, while July has been staying fairly flat. April has been increasing, March increasing, and December's been decreasing too. So using this decomposition makes it very easy in combination with season plots and subseries plots to get a better understanding of the seasonality, since we don't have to get confused with the trend anymore. It's a really powerful technique for visualizing your data. Oops. Okay, just give me one moment. Excellent. So let's go back to the slides and have a look at what we see. So we extract the decomposition components using the components function, and that gives you a decomposition table. And this works very similarly to a Sybil, but it has a different plot method that shows you the components. But you can still use any of these components with the existing tools that you have. If you just want to plot the trend, you can auto plot trend. If you just want to see the seasonality in the season year column, you can use season plots, GG season or GG subseries. So the auto plot gives you a decomposition plot, but we can also use this in other ways. Here I've shown the original data and the smooth trend cycle through the middle. So we should see that this component very closely follows the center of the data. Let me show you this plot in R as well. So here I have my decomposition. I can extract my components using the components function, but I'm going to come back to that. Starting with my original data set, Oz employment, I can create my plot of employed. The other way I could do this, of course, is that employed is here. In fact, I'll show you that way too. There's two ways that we can do this. Alternatively, we can start from the components and auto plot employed, which will give us a decomposition plot. But if you want a regular time series plot, you can drop the decomposition part and convert it to 8 Sybil. So now we get the plot of my data. But what I can now do is add extra information from this data set. So we have employed, but we also have trend, the smooth line through the middle. So I'm going to use geom_line, just regular ggplot, adding on some extra geometries. But my y-axis now is going to be trend. And I'll make some nice colors. Maybe I'll use steel blue. And I'll set the size to be a bit bigger. Oops, should be line width. But you can see I have my original data set that had seasonality, and then adding on the trend line to this plot, we get a nice smooth line through the middle of the data. There's many ways that you can produce the plot. The way I've chosen to show you here is slightly different from the slides. In the slides, we instead use auto layer, which is a way to add more time series plots from arbitrary data sets. So we've used the original data set for the original plot and then added on the decomposed trend using a different data set. We also see how to get a better look at seasonality using subseries plots and season plots. But another very useful variable, transformation even, we call it seasonal adjustment, is used very commonly for planners. If you're making big decisions, perhaps you're a policymaker, you often like to see the time series without the seasonality. And if we have an additive decomposition, it's very simple to calculate the seasonally adjusted data. We just take our original data minus the seasonality. Or equivalently, it's the trend plus the remainder. And this is so useful that if we go back to R, so commonly used, we can see that in the components of the data set, make this a bit bigger. In the columns of the components, we automatically calculate season adjust because it's so commonly used. So if instead of plotting the smooth trend line, I instead plot season adjust, maybe my line width is a bit too big here, make that a bit smaller. You can see I get the slight randomness, the up and down noise from my remainder component added onto my trend. And this blue line is a very common plot that you produce for decision makers. I think it's nice to also keep the original data underneath. It's perhaps some safety, because then you can compare the decomposition with the original data. It adds some additional context for what we see in reality. Now, we can, of course, calculate this ourselves. Remember, YT minus ST, or trend plus remainder, should decompose the data for seasonal adjustment. So let's try that too. If instead of season adjust, I use trend plus remainder, you'll see I get an identical result. And I can also do employed minus season year. These are all the same result. So there's 3 different ways that you can calculate the seasonally adjusted data. Now, if you had multiplicative decomposition, you'll need to divide by the components. And if you had log transformations, this is the one place where they're not automatically back transformed. So you need to be a bit careful when you report the results. If you've needed to log transform the data, just say this is the log transformed employment, or the log transform of the data that we're looking at. But for the trend component, this figure here, it's still reasonable to undo the transformation. So if you've got the log of the product, you'll end up with the sum of the logs. And if you wanted to focus on the trend component on the original data, you can apply the exponential function. Now, there are some parameters that you might have to play around with here. That decomposition that I showed you just now happened to work quite well. The trend was kept in the trend component, seasonality in the seasonal component, but that's not always the case. You might have to adjust the size of the windows to get a smoother or more flexible result. And to do this, we use the right-hand side of the formula. If you've used LM before, or cross-sectional modeling in R, you might be familiar with the model formula. On the left side of the tilde, this squiggly line, we have the response variable, the thing we're wanting to predict. That's employed. And on the right side, we have the method that we're going to use to make that prediction. And importantly, for the SDL decomposition, we have the trend and the seasonal windows. Let's have a look at these in R and see how that changes the result. So I had my decomposition here, but instead of just using the defaults, what if I use a trend window of 100? Let's make it really big. 100 here means 100 months. In fact, let's use 120. Then we've got a nice round 10 years. What this means is that we'll use one window between 1990 and 2000 and estimate a trend. So we'll have a straight line for this section. And then we shift it by 1 month to get the next 10 years starting from 1990 February, estimate a new line, which will be our trend. And the resulting decomposition, if I plot that with the components, sorry, decomposition, components, auto plot, you can see it will look a bit different. Give it a second. There we go. You can see my trend line is now incredibly smooth, but my remainder no longer looks like error terms. We've got some patterns in the remainder. So my trend window is too smooth. You need to adjust the window so that you get an accurate representation of the trend and cycle in the trend component. If I make it really small, maybe just 1 year, you can see it's more flexible than before, but it's still okay. It's a fairly smooth line going through the data, and the remainder looks pretty random. For symmetry reasons, we often prefer to use odd numbers. What if I make it even smaller, maybe 5 months? Now you can see the trend window is so flexible that we're capturing some of the randomness here. There's lots of little bumps. We don't want little bumps in the trend because trends should be a smooth pattern, a long-term trajectory for the data. So 5 is too small. So I think the sweet spot is maybe around 13, maybe 15. You can play around with that. Just like lambda, it's not very sensitive. So as long as you're close, it should be okay. The same thing can be done with the seasonality. Often we like to use an infinite window, or in the slides we used a periodic window. You can see periodic up here, which means the same thing. An infinite window means that we use a single window for the entirety of the data set. And that means that the seasonality doesn't change over time. So now you can see we have a single seasonal estimate that is fixed. Again, if I set a very small window, maybe 3 years, you can see the seasonality is allowed to change very quickly, but the remainder doesn't look very random anymore. So I've got too much flexibility in my seasonal component. The sweet spot for this might be 7 years. Let's try 7. There we go. It's allowed to change quite quickly, matching the patterns that we see in the data, and the randomness looks random. The remainder component is random. So you need to adjust these parameters, the window size, in order to get a good estimate of the decomposition. A trend window that gives a nice smooth trend that matches the ups and downs of the data, and a seasonal component that is smooth enough to not change very quickly. If you've got outliers, you can set robust equals true. Now, if you had multiple time series, like we've seen before, maybe holiday visitors to each of the states in Australia, you can do a decomposition on all of these time series at once. We'll see more of this tomorrow. You can then do sub-series plots on the seasonality. We've seen this already. You can do season plots. All sorts of stuff can be done with that. Okay, we are running out of time, so I'll quickly go through the remaining slides here. We might pick this up in the next session. If you have multiple seasonal components, remember the Victorian electricity data, we had a daily, weekly, and annual seasonal pattern. The STL decomposition can actually decompose all 3 or as many seasonalities as you have. And you'll notice that this is done completely automatically. And a word of caution, perhaps, for when you're transforming or adjusting your data, you are modifying the underlying data, and that can cause some issues. So there was a stuff up that happened in Australia, a mistake by our statistical bureau, the ABS, the Australian Bureau of Statistics, and it really caused some concern in the country because they said but the unemployment value had jumped. We had a large increase in unemployment, which is very uncommon. And this actually caused the Bureau of Statistics to stop doing seasonal adjustment for their data. They've since started this up again because they've found the problem and fixed it, but it's a nice story as a bit of a caution for what might go wrong. So the unemployment figures were wrong, and a lot of reports came out about this, a lot of concern. And this is what the time series looked like. So we've got the employed time series, was a monthly time series starting in 1978, showing a plot of this data. You can see we have a trend, maybe a little bit of seasonality, a bit tricky to see, but it's a fairly small seasonality if there is one. There's a cycle perhaps, but fairly simple pattern. Now, what worried everybody was this drop. Normally in August, you have this drop in August. See, in all of the other years, there was this slight decrease, and people were expecting this drop to happen again. But in 2014, it increased. Something went terribly wrong. Is this a genuine increase in the amount of employed people, or was there a mistake? Here's another way of plotting that data. So September minus August, the difference in employed people between the months. And you can see most of the differences is around 100,000, 150,000, but there was one change here where there was actually a decrease from August into September. There's an outlier here. This one dot represented the issue that got everyone concerned. And if I look at the SGL decomposition, I'll move over to the side here, you can see that there's a large anomaly in the remainder component. It usually stays pretty flat, but we had a sharp increase followed by a very rapid decrease, and it's this decrease that freaked everybody out. Another way of showing this is with a season plot. Normally you have August decreasing and then increasing, but this time we had the opposite pattern. So when the ABS produced their seasonally adjusted data, it looked horrible. Instead of that nice smooth flat line, the seasonal estimate was completely wrong. So we had a big increase in employment that made everyone happy, and then followed by a very sharp decrease that freaked everybody out. Now, what happened here is that every August, the Bureau of Statistics sent out a survey. And this survey asked all sorts of things, but it was pretty much, are you employed? And depending on what you answered, you'd have to answer a new set of questions, a supplementary quiz. And Australians tend to be quite lazy, and they knew that there would be more questions if they answered in a certain way. So what you would do is just say no to finish the survey faster and get on with your day. But something different happened in 2014. They stopped asking that extra set of questions. They decided it wasn't needed anymore. And suddenly Australians started answering truthfully because they weren't worried about answering the next set of questions. And this is why we had a sharp increase followed by a decrease in employment. So the supplementary survey conducted in August was changed, and people were avoiding this survey, but it didn't run in 2014, so Australians stopped lying. And this really impacted the ABS model for seasonal adjustment and caused a big problem. So they've now adjusted for this bias by adding some extra terms to their model for if they run a supplementary survey or not, and that fixed the issue. But just be very careful when it comes to doing your own decomposition, and this is why I really like plotting the original data, like we did up here. It's really nice to show the underlying data with your model's output, the decomposition, because it keeps sight of the original data. Because if you just show the seasonally adjusted series, it's vulnerable to errors like this. So be very mindful, choose the right seasonal windows and trend windows that accurately represent the patterns in the data. Otherwise, you can misrepresent what's happening underneath the surface. Okay, that's all we have for the first session. We'll take a 10-minute break and reconnect to continue looking at visualizing large collections of time series. I'll stick around for the next 10 minutes and answer any questions you might have in the chat. But other than that, get up, stretch, get a drink, and I'll see you in 10 minutes time. Many time series. Sorry, I'll just start again for the recording. Welcome back, and we're going to get straight into today's session. This session follows the previous one on visualization, and we're going to see our last main way of visualizing time series, and that is using the feature space. Using features to visualize time series is particularly useful for if you've got many time series. If you've got more than 6 time series or so, it becomes quite difficult to have a look at the season plot, sub-series plot, even just the time plot becomes difficult. You just have too many lines to show. Instead, we like to calculate features, which is a 1-unit summary of the time series. So we no longer have a time series, we just have descriptions of the time series, maybe how trended or seasonal that data set is. And then we can plot those points, those descriptors, which we call features, using cross-sectional techniques like a scatter plot, a box plot, many different methods here. And they give you a useful indication of the overall behavior in large collections of time series. And to calculate and visualize these features, we use the FEASTS package, which stands for Features and Statistics for Time Series. And in particular, we're going to focus on one specific type of features. There are many different features that you can calculate on a time series, and we'll preview all of them. But the STL features are of particular interest. They use the same STL decomposition that we saw in the previous session. However, they build on it in order to calculate these 1-unit summaries. If we're able to calculate the trend separate from the seasonality, separate from the remainder, that allows us to calculate some really helpful features like how strong is the trend, how strong is the seasonal component. And that tells us if we have trend or seasonality in our time series. And more than that, it tells us how much trend and how much seasonality we have. So we saw just before in the previous session, an STL decomposition is additive. We take our time series Y, and then we split it up additively into the components of trend, plus seasonality, plus remainder. Now with this decomposition, it's possible to calculate the seasonal strength by using 1 minus the variance of the residual divided by the variance of the seasonality in the residual. The strength will be close to 1 if we have a lot of seasonality, and close to 0 if we have very little seasonality. And we can do the same thing for the trend. We have the same variance of the remainder divided by the variance of the trend plus the remainder. This is my seasonal adjusted series. And this overall will be 1 if we have a very trended time series, and 0 if we do not have any trend. So let's have a look at the tourism data set. We've seen this one already, and I'll switch back to R so that we can look at this interactively. Here we go. So remember, the tourism data set was quarterly, and we had 304 different time series. And on day 1, yesterday, in order to plot this, we first had to do some manipulation. We maybe filtered the purpose to be holiday, and that gave us 76 time series, so still too many to plot. So maybe we calculated the total number of holiday trips to Australia, and then we plotted it. And from this plot, you can tell me that this is very seasonal. We have lots of up and down patterns, but it's not very trended. The trend, maybe there is some trend, it's increasing at the end, pretty flat at the start, maybe decreasing a little bit. But the strength of the seasonality is high, but the strength of the trend is low. So to summarize this, rather than getting that information from a plot over time, a time plot, we can instead calculate some features. So if I calculate the features using feat-stl, feat-stl is features from an STL decomposition like trend strength and seasonal strength, and features is what we use to calculate it. I've forgotten we need to add in the variable that we want to compute the features on. So we take our data set, pipe it into features, and calculate the trips variable STL features. And what this will give us is a table containing some summary statistics. It will tell us that the trend strength is 0.8, the seasonal strength is higher at 0.9, and the seasonal peak happens to be in the first quarter, while the trough is in the third quarter. So it tells us quite a lot of information. It also has other things that we won't get into, but spikiness, how straight it is, how curved it is, the error autocorrelation, all stuff that we don't need to worry about. But these are some useful summaries of the time series. Particularly nice is the trend and seasonal strength. What if I didn't add up, let me copy this. What if I didn't add up the total number of trips? Before I did that step, remember we had 76 different time series. That's too many to visualize all at once. But it is possible to calculate features on all 76 time series. And here we get, for the holiday travel purpose, the trend strength and the seasonal strength for all of them. And then we can plot this using regular ggplot. So on the x-axis, I'll put the strength of the trend. On the y-axis, I will put the strength of the seasonality, which is seasonal strength year. And then we can pick a geometry. I'm going to use a scatter plot. And what I get is a summary of the trend and seasonal strength in this data set. It looks like a lot of clouds of points, but each of these points represents an entire time series that I have in the data set. And in fact, I have 76 different points on this plot because I have 76 time series. Now we might be interested in what time series this one is. It doesn't have much trend and it doesn't have much seasonality. So maybe I take my features and then I filter the trend strength to be less than 0.3. Now I have just 4 time series that don't have a lot of trend. These are from various different places in Australia. We have outback Queensland, outback New South Wales, a small town in Tasmania, and a place in South Australia, the Barossa Valley. It's known for its wine production. Now, what I can do with this is plot them, of course. I can take tourism, filter the state to be Queensland. Actually, let's find what that one point was that I was talking about. So that one also had a very low seasonal strength, less than 0.25. So that corresponds to this one here. Less than 0.25 is the Barossa Valley in South Australia. So let's say region equals Barossa, purpose equals holiday, and that gives me the single time series that had very low seasonality and very low trend. Let's see if it was accurate. Let's plot the trips. And that doesn't look like much at all. We've got very random patterns, so the remainder term in the decomposition will be very high. Not a lot of trend, and I don't see any seasonality. Now, I could go through all 76 time series and look at them and make this judgment, but that will take a lot of time. So it's really useful to be able to look at all of the trends and seasonalities at once using features. Gives me an overview of the patterns that I have in the data. What about this point up here? It has a lot of seasonality, about 0.85, and a lot of trend, above 0.8. So I can use the same technique. We're going to filter out the time series, but this time my trend strength will have to be bigger than 0.8. So then I'll have this point and this point. Should have two observations. I've got the Western Australia's southwest and Melbourne, Victoria, the second largest city in the country. Now, Melbourne, Victoria is not very seasonal, which corresponds to this point here. And Australia's southwest in Western Australia has a lot of seasonality. So this point at the top corner here corresponds to the first row. Let's have a look at what that looks like. So filter region equals Australia's southwest, and the purpose was holiday. I can then auto plot the number of trips to this area, and hopefully we see a very seasonal pattern, lots of sharp up and downs, and it's got the highest trend of all the time series. So it's a useful summary of the big features in the time series, the trend, the seasonality, and more. And this is a useful way of understanding hundreds of time series in a single plot. Now, before I calculated just the features for holiday, the 76 different places where people could go for a holiday in Australia. But what if I cared about other reasons people might come to Australia? If they're visiting friends, if they're coming here for business, or some other reason. If I remove this filter as well, I'll copy this code first. If I remove this filter as well, so now I've got my original data set, all 304 time series, and I compute the STL features on this. As you might expect, it works as well. It takes a little bit longer because we've done an STL model on 304 different time series, and then we've calculated the components from that model, and we've extracted some useful features. So quite a lot of calculations have just happened there, but we don't have to write much code to do it. And then with these features, I can do the same plot. So let's put trend on the x-axis, seasonality on the y-axis, and use a scatter plot. And I'll give the plot a bit more space. Here we go. We've got a big cloud of points. We've got some time series up here which have more seasonality, and a lot of time series down here that don't have much seasonality in them. We've got some time series that have a lot of trend, which is beneath me. Move off to the side again. You see there's a few time series around here. And overall, there's not many time series that have a lot of trend and seasonality. But we have some more information here. Why do we have some time series that are more seasonal and others that are less? Let's have a look at our key variables. So in addition to our scatter plot, we can color the points based on the key variables. So we've got region, state, and purpose. Maybe people travel more seasonally if they're coming for a holiday. If I set the color to be equal to purpose, we've got 4 reasons people might come to Australia in this data set. Purpose is in red, green for holiday, blue for some other reason, and purple for visiting friends and relatives. And interestingly, you can see some separation in these time series. At the top, they're all green. And that's because people travel for holidays more seasonally when the weather's good. But when they come for business, they tend to come any time of year, whenever they're needed. So the business travel isn't as seasonal as the holiday travel. So when we're coming to creating models for all of these time series, if we're estimating holiday time series, we probably want to include some seasonal component in the model. But if we're thinking about business modeling, we might not need that seasonal component. The other reason in blue also seems to have low seasonality, but it's very spread out for trend. Some are very low trend, others have much higher trend. And for visiting, it's also more spread out, perhaps a little bit more seasonal. You can see some more purple points at the top here. There's a question in the Q&A. Using the strength test for an additive model, does the feature function also estimate the strength of the cyclical component? Somewhat. So in a decomposition, an additive decomposition, the trend component contains both the trend and the cycle components. So we cannot separate trend from cycles using an STL decomposition. So in some sense, the strength of the trend is referring to both the trend and the cycle, not just the trend. That's a good question. Thank you. Okay, we could also try plotting this by state. So if I color it by state, we'll see if there's any differences in how seasonal Queensland is compared to Victoria, maybe, the different states of Australia. There's of course more states to look at now. We've got 8 different colors to look at, so it's a bit tricky to see. I'm seeing some purple points, some green points up here. That's Victoria and Northern Territory. Perhaps a bit more seasonal, but it's all over the place. It's hard to see what's going on here. Maybe we can filter just the holiday travel now, and I'll do it before I calculate the features just to save a bit of computation. So now let's only look at the reason of travel being holiday. Perhaps it's more seasonal when you're going to Brisbane in Queensland or Victoria when it's cold. So in Victoria, we have some regions which are very seasonal, others that are not. We can tell that because it's purple. There's some purple points at the top and the bottom for high and low seasonality. For Queensland, in the green color, it's also a bit spread out, so it's not very obvious. Perhaps we can do some more summary. So now I'm going to group by country and, sorry, not country, by state, and calculate the total trips. So these pipe chains can get quite long and confusing, but you can break it up into different steps. So I first take all of my tourism dataset, but I don't care about the business travel. I only care about people going on holidays. And then I don't care about the specific area in Australia that they went to. I don't care if they were in South Australia, in Adelaide. I only care that they went to the state of South Australia. So I'm going to group by state and calculate the total trips to each state. So now I only have 8 time series to think about. And calculating the features on those 8 time series and then plotting them, we get an overall idea for how seasonal each of these states are and how trended they are. So Victoria, where it can get quite cold, that's where I'm from, is the most seasonal time series, and it's also very trended as well. Whereas Western Australia and New South Wales, perhaps, are less seasonal than Victoria because the weather is more comfortable all year round. Comparing that to the ACT, which is very low in the seasonal component, very weak seasonality, that's because ACT is only for government. No one goes to the ACT for a holiday, and so there's no reason for it to be seasonal. So I hope you can see some of the value in calculating these features and visualizing them. I think it's particularly useful for if you're working with hundreds of time series. And for your exercises that you'll be completing with your mentors, we'll be looking at the tourism dataset, and also we'll be looking at the medical dataset from Africa. And you've got lots of different regions that might have different patterns. So that will be useful to apply these feature skills as part of your analysis on that dataset. So in summary, taking a dataset that has many time series and computing one value summaries is a useful way of representing the patterns that might exist in large collections of time series. There is one part of this question that is relevant, and I'll come back to your question about transformations later. The second part of this question asks about the limitations in computing features, for instance, spectral entropy and the forecasting ability. So there are some limitations. For example, this STL feature is assuming that we can split up the data additively. However, as we've seen, if we've got multiplicative seasonality, that might not work very well. So perhaps we need to log transform the data first or apply some sort of transformation. Now that's possible. You can use the automatic Guerrero's method to transform the data and then do an STL decomposition and calculate the features, but it's a bit more work. So that's one of the limitations of the plots that are produced, and maybe why the seasonal strength isn't as high as it might be, because it's multiplicative rather than additive. So the features that we get are only as good as the model or the summary statistic that we use. And relating to your spectral entropy comment, if the spectral entropy is an accurate representation of how easy it is to forecast, then it would be a good feature. But it's not always the case where spectral entropy represents how simple or forecastable it is. Could you put that first part of your question in the Q&A again, and I'll come back to it at the end of the session. Okay, so here's a summary of what you've done. In addition to what we've seen with just simply coloring, it might be useful to facet by the different states and color by the purpose. And generally you can see that the blue points here, which if I move out of the way, represent the holiday travel, are more seasonal than other reasons of travel. So we've seen how to filter different time series of interest based on the features. Another way that you can do it is calculating the maximum seasonal strength here. So not using a greater than a certain value based on what you've seen, but just filtering the maximum. And then you can use a right join, which is an alternative way of filtering. So let me show you how this works. I'll switch back to R. As with any code, there's many ways to solve the problem. In the past, I was filtering out a specific location based on some threshold that I had. So here I had the two time series, one from Victoria and one from Western Australia. One had a lot of seasonality and the other had less. So I just picked the one that had the most seasonality, but one way that you can join in or bring back your original time series data is using join operations again. And this is a nicer way, I think. So if I call this tourism trendy holidays, and let's look at that. Tourism trendy holidays. I've now saved the features for trendy places to go, places that have a lot of trend, quite literally. And then I can take my tourism data set and I only want those two locations. So what I can do is a right join, which will keep the rows in the right data set, which is going to be tourism trendy holidays, and add in the information from the left data set, tourism. And I'm going to join this by the key variables. The key variables is just a general way of saying all of the keys, region, state, and purpose. You can, of course, also write, put this here for your notes. You can also spell them out yourself. So region, state, and purpose. Both will give the same result.
Then we can confirm with the second one.
So when we right join the data set, you can see we now get a Sybil again, but this time I have both time series that was from my trendy locations. And I can plot this by plotting the trips variable. And you can see the two locations plotted against each other. So you can see they both have quite a lot of trend, but the blue line has much more seasonality than the red line. And this is consistent with the features that we calculated before. Remember the seasonal strength of Melbourne, which is shown in red, was very low, so we don't have much seasonality. But the blue line in Western Australia had a lot of seasonality. The other way that I like to join two datasets is to use a semi-join. And this gives the same result. But there's a slight difference in the dataset that we're plotting. Instead of having all of the extra information, like the features that we've calculated, trend strength, seasonal strength, curvature, and so on, we now only have the rows, the columns from the tourism dataset. Let's compare that with the right join. The right join will keep both sets of columns from the dataset, which might be useful. But because we've got the time dimension here, we've got a lot of duplicate information. The seasonal strength and the trend strength are showing up many times where we don't need that. So I usually prefer to use a semi-join. So we can also use this to calculate the maximum trend, which happens to be this time series. All of the data sets here don't have a linear trend, so the trend component is not as strong as other time series. And here is all of the features from the STL from the series in tourism, but this time we're using a different set of features from the ACF. So if you remember the ACF, let's have another look at that. Let's take these two time series. Remember yesterday we calculated the ACF, and the ACF was a useful summary of all of the information in the dataset. I can plot the ACF for both of these. You can see the trended time series in Victoria. This one's also trended, but not as much because it's mostly positive and decaying, but they're both very seasonal. You can see the seasonal lags here having peaks. Sorry, Victoria one is less seasonal. The peaks aren't as strong. But these ACFs, the values of the ACF, also provide useful features to us. The strength of the first lag is a useful feature. Maybe the seasonal lag 4, how big is that? That's a useful feature as well. So what we can do for these time series is calculate features of trips and feet STL. Feet, let me go back to the slides and have a look. Feet ACF. So you can see the first lag for Western Australia was 0.322. See that value, 0.322. And the holiday Victorian Melbourne location ACF1 was a bit larger, 0.644. ACF10 represents the sum of the first 10 lags. And this is useful to see if it's all positive. You can see for Melbourne, where it was slowly decaying and all positive, the sum of the first 10 lags is 3.83, very big. Whereas for Western Australia, it was a bit smaller, 1.41. And we've got the seasonal first lag of this one, 0.777, and Melbourne, 0.676. So all of these features provide some information about the patterns in the time series. We also have autocorrelations on the differences of the data, which will become more informative on day 4 when we look at ARIMA modeling, which uses differences to simplify the data, much like we've used log transformations to simplify seasonality today. So there's many different types of features that exist, and it's not just ACF features and SDL features. So if we look at the features help function, you can see that a list of features available can be found in these links. So if we click on features by tag, we can see a list of all of the features that are available. We've seen only a few of these. We've seen ACF features, which is ACF and autocorrelation tagged. There's also partial autocorrelation functions, which we'll see in the ARIMA topic on day 4. We've seen Guerrero's method for automatically computing the transformation parameter lambda that's needed to regularize the variance. There's some counting features, decomposition features that we saw today, some for intermittent time series, some for formal statistical tests. There's all sorts of features that you might like to use to summarize the information of your data. And what we might like to do is cluster our time series based on similar patterns. If we can identify clusters of time series, then we can use a similar model to forecast them and a different model for different clusters. So this makes it much more feasible to produce reasonable models for many time series. So we can use the feature set function to create a list of all of the features that are relevant to a certain topic. In this case, I'm calculating all of the features that exist in the package feasts. So if I go back to R and use the feature set function, I can set packages equals to feasts. And then what we'll get is 21 different features that exist in the package. And this feature set can be used with the features function to calculate all of those features. And as a result, we'll end up with 51 columns, 48 different features on the time series. Probably too many for us to look at, but we can use dimension reduction techniques to combine them together and produce a useful new feature that separates the information in each time series for clustering. Okay, going back to R. Now this will take a bit of time to run, especially if you don't have a powerful computer. But I will use the same features function on the trips variable to calculate all of the features that exist in the package. And because this will take a while, I'm going to save it. Okay, while that runs, we can have a look at the slides to see what we'll get. So what you should see when this finishes running is lots of different columns, all describing different patterns that might exist in the dataset. And as I mentioned, it's probably too many for us to look at. You might pull out some interesting ones like trend strength and seasonal strength. But what's more useful here is to apply principal components decomposition. How many people have heard of principal components? Maybe you can put a little hands up or something, a reaction to represent that. Okay, a few people have heard of principal components, but I think it's worth explaining. Thank you. So principal components is a way that we can combine multiple columns together and reduce their dimension. So rather than having 48 different features, we really just is a very simple way of explaining it, I suppose, very rough way. Instead of looking at all 48, we find the most interesting bits from all 48 columns and rearrange them so that the first 1, 2, 3 variables represent almost all of the interesting parts of all of the 48 variables. Now their meaning becomes a lot more complicated. It's not like we can look at trend strength and seasonal strength and say, this is a very trendy time series, this is a very seasonal time series. But principal components is useful for clustering. We might not know why they're similar, but we can, based on the features that we've used, say that they have similar patterns. And then we can visualize these principal components to see those clusters. Okay, a little warning here, but that's fine. What we should have is a new data set with 51 features, and we've got 51 columns, I should say. 3 of those columns are the key variables, so that we have 48 different variables in total for our features. And then what we can do is remove my key variables because they'll cause problems for the next model that we're using. So remove region, state, and purpose. So now I've just got a data set with a lot of numbers in it, all of my features. And then I can use the PRComp function in order to calculate my principal components. Now, because these features are all on different scales, some of them are numbers between 0 and 1, others are variables that could go into the hundreds. It's important that we scale our variables. So I'm going to set scale equal to true. And what I will get from this is 48 principal components. These principal components are rearrangements of all of the different variables that existed, all the different features, in a way that the most interesting ones, the ones that explain the most variance, happen first, and the ones that explain the least variance are right at the end. So we don't really care about principal component 46, 47, 48. What we really care about is the first 2 or 3. And then we can add these principal components back onto our original feature dataset by using the augment function from the Broom package. This will give me both my features and my principal components, which will make it really nice when it comes to plotting and looking at the data. So to finish this, we use Broom, augment, put in the data set that we're augmenting, and now I have 100 columns. The first 3 columns, or even the first 4 columns, are metadata, the regions, the key variables, and the row names. The next 48 variables are my features. And then right at the end, which isn't even shown here, I have my principal components. So I'm going to save this. as tourism principal components. There we go. And now we can start visualizing those components. So let's use ggplot. Principal component 1 on the x-axis, principal component 2 on the y-axis. And then use a scatter plot. It's not principal component 1. Let me check what it was called. It's called .fitted PC1. So let me fix that. .fitted PC1, .fitted PC2. Okay, that's an interesting looking plot. Can you tell me anything about this plot? Is it meaningful at all? It's a bit tricky to answer that because we don't know what principal component 1 on the x-axis and what principal component 2 is. But what we can see is that in these two dimensions, there's a lot of time series that are similar around this cluster, some that branch out in this direction, and others that branch out down here. What will be more useful is to add some color. Maybe some of these principal components relate to the purpose of travel, for instance. So just like we did before with the trend and seasonal features, let's color this by the reason they came to Australia. Now we have something interesting. You can see that the first two principal components, PC1 and PC2, have separated out the holiday travel from the other reasons of visiting. So there's probably a lot of seasonality embedded in principal component 2, because vertically, the high seasonal values are separated from the low seasonal values. Now you can, using some principal component stuff, figure out the ways that these principal components are built, the coefficients, but that's not so important. It's more important to look at the clusters and separate it out. Maybe it also relates to state. So let's color by state this time. And you can see this is less separable. So state isn't as different. What this says is that regardless of where in Australia, the travel is more similar in terms of the patterns that exist in the data. So it doesn't matter if you're in Tasmania or Victoria, there are some time series that are similar. There's some overlap there. With principal components, because we scaled the data, it's useful to set the fixed aspect ratio. I should have done that. And we can color by the different key variables to see if there's anything that separates them. So state, there wasn't much separation, which said that the time series had a lot of overlap between the states. The regions had a lot of similar patterns. But when we color by purpose, you can see some time series, the holiday travel is looking very different from the rest of the time series, the rest of the purposes of visiting. Just like before, we can isolate some interesting observations. We can look at this and find some outliers. So you can see this point and this point are outliers. And if I move out of the way, you can also see there's a couple more points down here. So if the principal component 1, the x-axis, exceeds 10, we've got some 4 weird observations. I wonder what these look like, because these, by the principal components, don't look like any other time series in the dataset. They're very unique. So let's use the same tools that we did before to find out what time series these are. We have our principal components, and let's filter .fitted PC1 to be greater than 10. So ideally now, we've got only the right side here, greater than 10, which will separate these 4 points, these strange outliers. And sure enough, we get 4 resulting rows with the region, state, and purpose that match. And most of these happen to be holiday travel. So these are our outlying time series. So I'll save that here. And just like before, I'm going to use a semi-join to bring in the original data. So tourism, pipe into semi-join, and the data set that I'm going to match with, the outliers. So I saw a question before that Bahman answered in writing, but I'll bring it up again here. A semi-join is the most useful type of join for filtering the data. And what it does is keeps only the rows in tourism which match the rows in outliers. And how are we going to match them? We're going to match them using the key variables. That is region, state, and purpose. So when I run this code, I end up with just 4 different time series. And these are the time series from tourism, which only has the trips variable, that exist in my set of outliers, in my 4 outliers that I looked at. And once I've got this time series, I can then plot it. All of the tools from yesterday for visualization we can use to look at these particularly interesting time series. I'll bring the code back shortly. So here we can see some of the time series, like South Coast New South Wales holiday is in the green line. This looks very seasonal. This is probably the most seasonal time series in the entire data set, which is probably why in the principal components, if I had to guess, New South Wales was this orange one. You can see how that's the furthest out in this direction, because this direction is seasonal, is the most important factor in the principal components. So this one is unusually seasonal. It's really strong in terms of its seasonality. What about perhaps this purple one? Sorry, I'm blocking that. This purple one for Victoria. So let's go back to our next plot. What makes that special? The Melbourne time series, Victoria, is in blue. It's not this purple line. The time series colors are different. So this blue line is very trended. See that strong trend? But it doesn't have much seasonality. And in this data set, most of the time series don't have trend. They're usually pretty flat and increase, very similar to this red line here. No trend, and then increase at the end. Whereas this blue line is unlike any other time series in the data set because it has this increasing pattern throughout almost all of the history, has a very strong trend. The other purple and red one, probably interesting for other reasons, but it's not so obvious. This one doesn't have much seasonality at all. This one seems pretty ordinary to me. What we're probably seeing with those ones is that they're these two down here, I think. They're similar to each other. So I can't quite get out of the way. There we go. These two here. Okay, so once again, for the join operations, we use a semi-join to filter the data based on matching rows. So we want to match these regions, states, and purposes. That's why set by equals those variables in this tourism data set and keep only those rows. So that gives me my 4 time series. A right join keeps all right data sets, data rows, and adds left data rows that match. So what that means is if I did a right join, I'll be keeping all of the rows from this data set, my 4 rows, and the columns, the 100 columns. And what I'll be doing is adding on the matching time series to that data set. So you'll see we keep all of the feature information, which we don't really need. That's why I prefer the semi-join here. But we still do have the trips variable that we can plot. A left join is very similar, but it keeps everything in the left and adds from the right. So I'll show you both of those in the code that I will provide later. So in this case, the semi-join and the right join makes no difference to the plot that we get. But it does have a difference to the data set that is produced. We just happen to not use that extra information when we use the right join. Okay, so principal components are particularly useful for finding clusters of similar time series. And these similar time series, we can look at a few of them and see what most of them will look like. And that allows us to produce models for specific clusters. It's also useful for finding outliers and having a look at them, which is also useful for if you're looking at large collections of time series. Maybe you've got lots of hospitals, maybe you've got lots of computers, and a hospital or a computer isn't working very well, or is acting strange, not like the others. You can use this technique of calculating features over time, and then principal components to reduce the information, reduce the dimension, and then look for these strange hospitals or computers that aren't performing properly, and then investigate further. So it's a very powerful technique for analyzing time series where there's lots of data sets. There's another question in the chat. Which bit of code rounded the outliers? That's a good question. All of the code for this for the slides are available on the GitHub repository up here. You can click on GitHub. And when you download that repository, it'll look like this. So let me show you the GitHub repository. So here's the GitHub repository. You've got all the folders. All of the slides are stored in the materials folder. So currently we're working on the features slides. So you can find all of the code to produce all of the plots and slides here. And in particular, the rounded figure should be here. I've not looked at this for a while, but the code should be all here. And if not, do you have my email? You can send me an email and I can help you. But essentially, we can highlight them. Let me switch back to R. So I've got my points here. I can add on a different set of points for a different data set. This data set will only have large PC1s. So these are the 4 outliers that I want to add to my plot. And if I add them to the plot with a really big dot, you can see I can outline them. As for making the rounded point, that's just changing the style for these points. And it was done underneath the first set of points. So if I rearrange the order to do the outliers first and then add the colorful lines on top, I get a black dot with a green color to highlight them. That's very similar to how we've done that slide. Thanks for the question. Looks like there's a few questions here. So I think we've got enough time for all of them. Just check the slides. Yeah, we've just got one last slide. So I'll do this slide and then I'll get to all of your questions. So this last slide is just showing the outliers that we've extracted here based on the first principal component. If PC1 is larger than 10, then we determine that to be an outlier. and we can plot them separately. Here in the slides, we've used facets. What I've shown you in the code is just plotting them with different colors. You can use many different techniques to show these interesting time series. Okay, we have finished very early. We've got 30 minutes before we need to finish. So I've got heaps of time for questions. I'm going to stick around and answer them. Otherwise, you can enjoy an extended break. And some of you with the Australian mentors will be having your mentoring session shortly after in about an hour's time, 50 minutes.
Mitch, I think a couple of people, they have, I think, difficulties actually using materials. So I was wondering whether
Yes.
it's worth actually maybe going through the website and just demonstrate how they could use the materials, including the one you showed actually in GitHub, but also maybe running the first code in the setup. I think
Of course.
that's something that I realized, through some messages in the Slack, that people missed those kind of setup things. So that would be, I think, very helpful.
Great. Maybe I'll do that first, since it's perhaps most important, and then I'll get back to the questions about principal components and features. So for the exercises, we have our Forecasting for Social Good website, the workshop, and I've just put the link to that in the chat. On this webpage, there's all sorts of information, but most important, we have the software that needs installing. But for your exercises, when you've got the data set, when you've got the tasks to complete on your own and with your mentor, this part here, you can find the exercises on the website by clicking on Schedule and then clicking on Exercises for that day. So this is yesterday's exercises. If you haven't done them yet, don't worry, you may not have met with your mentor yet. It depends on your individual group for when you'll be meeting. If you don't know when you're meeting, then you should get on Slack and ask your mentor in that group. So in the exercises, a very important chunk from the first day is this setup chunk. And what this will do is provide you with some starter code to answer the questions, and it will include all of the data sets. So if you're having trouble finding the data set for the apply exercise, vaccineadministered.csv, that's because you haven't completed this first setup chunk. So I'm going to copy this code and run it in R. So I've just pasted it into my console. I guess I need to update the link for this. It'll still work, but you'll get an old version of the exercises that doesn't have the data. I think we've found the problem. Okay, I will fix this as soon as we're done here. Sorry, that was my mistake. We changed the website around a little bit. Forecasting for Social Good.org/AFRICAST. Okay, I'll update that URL in the website. My apologies for that. I've put it in the chat now so you can follow along and get all of the exercises for your lab sessions. If you run this code, it will download all of the lab exercises and the data sets that you need. This might be why you weren't able to find the data sets, so I'm sorry for that. So when you run this line of code, it will suggest where it will download it into. In this case, it's just putting on my desktop. That's fine by me. You can also put it on your desktop, then move it later, whatever works for you. So I'm going to say, yes, I agree. This is random. You'll have to read it and agree to download it in the right place. And then you'll find that it says it's downloading from the website. It successfully downloaded a quarter of a megabyte, and then it has unpacked the zip file to get access to the dataset. And then the last question is, shall we delete the file, the zip file? Yes, we don't need that anymore. And then you'll see it says it's deleted the file and it's opening the project in a new window. So give it some time to open the new window. And I'll need to find how to switch to it. Here we go. And then what you should see here is a new art project that was opened up called Exercises, which has day 1, 2, 3, and 4, and 5, the daily set of exercises. And importantly, you have your data in here too. So this data set includes the vaccine administered CSV for the apply section, and also some data sets that we use in the labs. So if you click on the day that you're working on, day 1, the idea behind this is that you work through these exercises. You'll see there's some question marks that we have provided for you to fill in, figure out what goes where, and work alongside the website. So in the website, we'll guide you through creating a Sybil, for example, and give you some code. You can copy this code and bring it into RStudio to try it yourself if you like. I will add a new chunk here using this +C button and pasting my code. And you can try running this code for yourself. So you can see it's created Guinea rice, which is in my environment, and I can see the data. Continuing on with this exercise, which you'll do with your mentor, you'll see there's some guidance between some problems you might encounter, but there's also some tips for some common things. So we talked about how the key variables like state is often a character variable. So there's a tip for that here. And the measured variables, takings, occupancy, and CPI, are almost always numeric. And then sometimes we have some questions. So these questions you don't need to write down. You're welcome to if you like. But which of these variables identifies the time series? In which case, this is asking what are the key variables of the data set? And importantly, there will be some sections of the output that says your turn. You'll have a little construction code. And when you come across these your turn sections, this is where we have some code in the exercises project for you to complete. So the your turn section said create a Sybil for the number of tourists visiting Australia from the tourism.csv dataset. And in Australia, in the project, we have the same instruction and some code to get you started. So you replace the question marks with the appropriate function that you need to use. I think I see a few errors in the chat. Unexpected / in HTTPS. I'm guessing that that's an issue with Zoom. Maybe it's copied it a bit wrong. Let me try copying this myself and running it here. Directly from what I gave you in in Zoom, sorry. No, that seemed to work for me. This is something that you might have to work on with your mentor. You've definitely put quotes around it. Could you copy the code that you've tried to run and put it in the chat?
Mitch, is it helpful if we ask one of the participants to share the screen? And
We could try that. We'll start with the line of code, and if that doesn't help, we can try and share the screen. It seems like this is a common error, so it'll be good to get this solved today. We've got the time in the session to fix this now.
So from who is volunteering to share the screen? Is it Agnes? Do you
It's
want...
okay. We'll start with copying the code, and if that doesn't work, we can share the screen. Could you copy the code that you put into R that gave you the error? And Bahman, could you try running that code on your computer? See if you can encounter that too.
No, I mean, the thing is, yeah, you have to type the entire thing. Use this, not just the HTTP. You have to type all this. I mean, copy all this and paste it as Mitch did in this. It's not just HTTP part.
So if you just have the link, let me show you that in R. If I just copy the link and put this in here, I get that error, unexpected / in HTTPS. What you need is to use the entire line of code. So we've got use this, use course as our function, and then in quotes, we have the link to the course materials. So you'll need to put this entire entire line of code into the console. Let me know, try that out and let me know if you're still having issues with that. Now that's another problem that you might encounter. So if you've run into an error that says error in load namespace, there is no package called use this. This tells you whenever you get this error, no matter what it says here, it says that you don't have a package installed. And it's so helpful, it actually tells you what package you need to install. In this case, it's saying we need to install the use this package. And you can install that if it's not currently on your computer using install.packages. And I'll put that in the chat for you as well. So if you run install.packages, and I'm going to not restart so that I don't lose some stuff, then it will install use this, which is needed to run that code and set up the course for you. Okay, okay, so there's another issue in the chat. Just wait for use this to install. When you install use this, you should see at the very end, it'll say done. There we go, done. So it's installed, and then you can try running the code again. There was another problem posted in the chat. Running this code, you get this error. Download does not have MIME type. If you get this, then it's because you haven't written or haven't used the entire link. So here you've got /AFRICAST. You need exercises.zip on the end. You may have missed that from the code that we've put in the chat. So I'll put the code in the chat one last time. And you can try that again. Don't forget to include exercises.zip. And let me know if you're still encountering some difficulties. Still not working for you, let me know. It's really important that we can all get access to these exercise materials so you can work through them with your mentor and also have access to the data. Okay, there's another comment here. And in this case, you've got all of the code right, Edson. You just need to enter 1, 2, or 3 to whatever that says yes. So in your case, it says number 3, I agree. You need to say yes. So you have a very similar message to what I'm showing here. Is it okay to download it onto your computer? Type definitely, or I agree, or whatever matches on your computer. It's not always 3. And then say yes again. In this case, it's 3 again for me. If you answer the prompt with 1, 2, or 3, it will open it up for you. It's working for you now? Do we have anyone else having trouble downloading the course materials for the exercises? Yeah, it will give you a prompt. It will ask you if it can download it for you, and then if it can delete the zip. Just say yes to all of the prompts, and then it should work for you. To specify a new directory, it's easiest to just download it onto your desktop and then move it on your computer using your normal file browser. If you want to download it into a different place, you can use dest equals wherever you want to put it. So you can say download it to my downloads folder, for example. But I'd say just keep it simple. Put it on your desktop and then move it later. Okay, seems like there's some other problems with keeping the package installed. Michael's having some issues with unexpected symbols. It looks like you're having that issue with the plus. Remember how I showed you before, when you have the plus showing up, it means that you've got some incomplete code. In this case, I've opened a round bracket and a quote, but I've not closed it, so it's waiting for more code. You'll need to press escape, that's ESC on your keyboard in the top left, to stop waiting for more code, and then you should see an arrow. When you have the arrow, make sure you put in the entire line of code, including the end bracket and the quote. And then when you have the entire line of code, run it, and you should get the prompts to install it. Okay, it's strange that you're only getting day 1 to day 3. Perhaps you're not downloading it from the Forecasting for Social Good website. We've got an updated version from the link that's, unfortunately, and I will fix this, we've got a different link from what's shown in the code up here. I will update that tonight. But the correct link is workshop.f4sg.org/AFRICAST. So I'll put this in the chat of Zoom again for you. So if you don't have all 5 days of exercises, try using the course again, downloading the course again from this link in the chat. Once you've got this new window open, the exercises project, then that's all that we need to do for today. You can start looking at day 1 and day 2 alongside the exercises from day 1 that I've got here. And in day 2, these are the exercises from today, where we'll try out doing some transformations, like the log transformation, CPI transformation, and some decomposition. So we do the STL decomposition in the exercises as well, various plots of this, and the features. So you can start working through these exercises, and we'll be doing this along with our mentors as well during the exercise sessions. So that's with the time that you are organized with your mentors. So whenever we use a data set here, you can access the data set from this project as well. So the data is contained in this folder. That will make sure that all of the code from the website should work on your computer. So for instance, in the first set of exercises from day 1, you can see we load in the Guinea rice dataset from the data folder. You need to be in this project in order to access that dataset. So if you see exercises in the top right corner, that means that you have a data folder which has Guinea rice. If you don't see exercises in the top corner, you can click on it and then you'll see all of the projects that you have. So you want to click on exercises to switch to that project. Is anyone else still having difficulties setting up their exercises?
Just to reiterate what Mitch mentioned multiple times, you have to work alongside the website, basically, because the website describes both learn and apply. So you open the website first, start from the beginning, read, take notes, do whatever you want, and then at some point you will see your turn. Okay, so when you see this your turn, it means in the learn part of the exercise in RStudio, there is a chunk of code that you need to complete, right? And here we go. So there is a chunk of code. So when you see your turn, it means there is a chunk of code in RStudio here in day 1, day 2, day 3, day 4, and day 5. And once you complete the learn part, you will see now some questions in the apply part in the website as well. So you have
in the website, yes.
In the website, and then the couple of things that you need to do with the vaccine data set.
So you've got lots of plots to learn about, and then when you finish learning about them, you can apply it to your African data set that we'll be looking at, the medical data set.
Yeah, so here
we have a big your turn section.
Absolutely. So here, like in the learn part, there are a lot of explanations of different important things. So hopefully by doing that, you learn, in addition to what covered today, you learn more things, and now you can use what you have learned to apply in this data set. And again, if you go to the RStudio exercise project, again, you will see that there are also some explanation alongside the apply exercise, because again, that helps you to understand better the sort of thing you have been asked to do, or the sort of thing that you need to do. And every time you need to complete a chunk of code, you see this question marks. It means you need to fill in those parts, basically.
So like we saw in day 1, to create a Tibble, we start with our data set that was created earlier in previous chunks, and then which function is needed to convert a Tibble into a Tibble. So that would be as Tibble, similar to what we would have talked about in the learn section. Oops, with 2 B's. What are the index variables and what are the key variables? So it's all about filling in the blanks, the question marks. And then when you finish filling in the question marks, you can try running your code to see if it worked. Okay, if you're still having some difficulty setting up the exercises, please send us a message to your mentor or to us on Slack, and we'll try and help you out, make sure you get it downloaded, because it's important that you have access to these exercises to be able to complete the exercises with your mentor. And of course, have access to the data set here. Other than that, I will finish answering the questions about today's material for feature analysis. And I think that's all we have for today. So let's go back to the questions. So the first question here is about PCA. That was our principal component reduction. Let me go to the slide for that. So we calculated the many features, and then we calculated principal components on those features. The question asks, should these features, trend strength, seasonal strength, the peak, the trough, the linearity, all of that, do they need to be related? Not really. And in fact, often it's better that they're not related, because what we're looking for is that the features present something new about the data, some added information that we wouldn't have seen just by looking at trend and seasonal strength. If all of the features are related, if all the features are very similar, then when we reduce the dimension, there won't be much information to look at. We just have 1 or 2 dimensions that matter. Having a lot of features that are diverse and look at different aspects of the time series is important. That gives us good principal components, which provides a very clear separation of the time series so that we know which are similar and which are not. The relatedness that's important is because all of these features are applied to the same data set. That's a good question. Thank you for that. The next question I have here is, in time series plots, can we use a scree plot to determine the number of components to retain for our analysis? Bahman, do you want to answer this one?
Yeah, yes, please. Yeah. So sorry, do you want me, or I'm just typing?
Yeah, could you, for scree plots and number of components? It's been a while since I've looked at scree plots. That's for variable importance, isn't it?
Scree plots. I don't. Sorry, I haven't used it myself. What is that? Can
I'm
we do it
pretty
with?
sure it's this.
Is
Let
it
me
with
see.
table?
This exposes how much of a time series person I am and not so much a cross-sectional dimension reduction person. So here's an example of a scree plot, and I'm pretty sure it is what I think it is. Correct me if I'm wrong. But this shows the principal, oops, I'm sharing the wrong screen. Sorry. Let me take the principal components that we're looking at for, actually.
Mitch, we see the
You're seeing the wrong exercises. Yeah. One moment. Thank you for pointing that out. Here you go. So we had PR comp here. Scree plots. The short answer is yes. So we have our principal components from our features of the tourism, and then we can use a scree plot to visualize those principal components. And the way that a scree plot visualizes them is by how much of the variance is explained by each principal component. So here it's saying that the first principal component and the second principal component of our dimension reduction explain lots of information. We've got very big bars here, but the ones afterwards are suddenly a lot smaller. They're still big enough to consider and include, but you're right. At a certain point, these scree plots, these bar charts, will get so small that they're not providing any useful information. So you can use a scree plot. You can use a scree plot to identify how many principal components are useful. In this case, the first two you would definitely want to consider. And if you really wanted to look a bit deeper, you might consider the third, fourth, and fifth, maybe even more. But definitely the first two, because after that, the variance drops substantially. That's a great question. Thank you for that. Okay, I've finished the Q&As. Did anyone have any last questions before we close out? Bahman, did you have any final words?
Not really. I think we can maybe stop the recording first.
Okay, fantastic.